Hello, Assalamu alaikum. Today I want to continue this chapter 20.4, the connection between electron transport and phosphorylation. Now, some of the energy released by the oxidation reactions in the electron transport chain is used to drive the phosphorylation of ADP. As I told you before, that the phosphorylation of ADP to ATP requires 7.3 kilocalorie. And in chapter 19, we saw that, or in this chapter, we saw that each reaction catalyzed of 3 of the 4 respiratory complexes provides more than enough energy to drive this reaction. You remember through complex 1, complex 3, and complex 4, but not through complex 2. Now, the energy-releasing oxidation reactions give rise to proton pumping and a pH gradient across the inner mitochondrial membrane, which is used to drive the phosphorylation of ADP. Now, differences in the concentration of ions across the membrane generate a voltage gradient. So in addition to the pH gradient, we need something called a voltage drop. So coupling process converts the energy of the electrochemical potential voltage drop across the membrane to the chemical energy of ATP. Now, a question, what is the coupling factor in oxidative phosphorylation? Now, a coupling factor is needed to link oxidation and phosphorylation. There is a complex protein oligomer, which is separate from the electron transport complexes, serves this function. It is needed to link oxidation and phosphorylation, and it's called ATP synthase. Now, the complete protein spans the inner mitochondrial membrane and projects into the matrix as well. The portion of the protein that spans the membrane is called the FO. And it consists of 3 different kinds of polypeptide chains, A, B, and C. And research is in progress to characterize it further. Now, the portion that projects into the matrix is known as F1, and it consists of 5 different kinds of polypeptide chains in the ratio alpha 3, beta 3, gamma, delta, epsilon. طبعا this is the site of ATP synthesis, whereas FO is the site where proton entrance. Then proton return to the matrix through the FO unit of the ATP synthase. This enzyme, ATP synthase, is also known as mitochondrial ATPase because the reverse reaction of ATP hydrolysis as well as phosphorylation can be catalyzed by the enzyme. Now, the hydrolytic reaction was discovered before the reaction of the synthesis of ATP, and that's hence the name. Now, in the 1997 Nobel Prize in Chemistry was shared by an American scientist and a British scientist for their elucidation of the structure and mechanism of this enzyme. Also, the other half of the prize was given to a Danish scientist for his work on the sodium-potassium pump. Why? Because it also functions as an ATPase. Now, this is the schematic representation of ATPase, or as you can see, then this is model of the F1 and FO components of the ATP synthase, a rotating molecular motor. Now here you see, here we have the so-called the FO unit. Now the A, B, alpha, beta, and delta, these, they constitute the stator of the motor, whereas C, gamma, and epsilon subunits form the motor itself. Now, flow of protons is through the FO unit of the enzyme or the complex. Now, flow of protons through the structure turns the rotor and drives a cycle of conformational changes in the alpha and beta units that synthesize ATP. So where does ATP synthesis occur? In the F1 unit of the enzyme. From where protons enter through the FO unit of the ATP synthase. Note these two informations. Now, compounds known as uncouplers inhibit the phosphorylation of ADP without affecting electron transport. A well-known example of an uncoupler is a compound called 2,4-dinitrophenol. Then we have various antibiotics such as valinomycin and gramicidin A are also uncouplers. Now, when mitochondrial oxidation processes are operating normally, then electron transport from NADH or FADH2 to oxygen results in the production of ATP. This is the normal situation. However, when an uncoupler is present, one of these, oxygen is still reduced into water, but ATP is not produced. So this is, you uncouple oxidation from phosphorylation. However, the effect of uncouplers is temporary, since if the uncoupler is removed, then ATP synthesis linked to the electron transport resumes. Now this figure shows you the structure of these uncouplers of oxidative phosphorylation, namely 2,4-dinitrophenol, you see, an aromatic compound. Here we have repeating unit of valinomycin. لاحظوا أن الفانيلوميسين is a cyclic trimer of 4 repeating units, ABCD, ABCD, ABCD connected together. And this is a key for these letters: A for L-lactate, B for L-valine, C for D-hydroisovalerate, and D for D-valine. Now, the other antibiotic called gramicidin A consists of 15 amino acids, as you can see, with alternating L and D amino acids. You remember when we talked about amino acids, we said naturally occurring amino acids have L configuration. However, the amino acids can be found in antibiotics, and these are examples, and in the bacterial cell wall, as we mentioned before in chapter 16. Now, also there is the so-called, a term called the PIO ratio is used to indicate the coupling of ATP production to electron transport. And the PIO ratio gives the number of moles of Pi consumed in this reaction in the phosphorylation of ADP to ATP for each mole of oxygen atoms consumed in this oxidation reaction, where Oxygen is the oxidizing agent, but it is reduced to water. As we have already mentioned before, 2.5 moles of ATP are produced when 1 mole of NADH is oxidized to NAD+, and 1.5 moles of ATP are produced when 1 FADH2 is oxidized in the electron transport chain. طبعا these experimentally determined PIO ratio, experimentally determined values. Then 2.5 when NADH is the substrate oxidized, and 1.5 when FADH2 is the substrate oxidized. No, these and these are the one these values are the one that we use in order to calculate the number of ATP produced from the complete oxidation of glucose, etc. Now, a summary of this connection between phosphorylation and electron transport. Now, coupling of electron transport to oxidative phosphorylation requires what? The complex protein oligomer ATP synthase. By the way, this ATP synthase, sometimes it is called complex 5. It is separate from the 4 membrane-bound complexes 1, 2, 3, and 4. Sometimes they call this complex 5, remember. Now, this enzyme has a channel for protons to flow from the intermembrane space into the mitochondrial matrix. As I show you, protein flow is coupled to ATP production in a process that appears to involve a conformational change of the enzyme. Now, the first part here occurs through the FO unit of the synthase, and the second point here occur in the F1 subunit of the ATP synthase. Now we want to talk about the mechanism of coupling in oxidative phosphorylation. Now, several mechanisms have been proposed to account for the coupling of electron transport and ATP production. Now, the mechanism that served as the point of departure in all discussion is the so-called the chemiosmotic coupling, which was later modified to include a consideration of conformational coupling. So, chemiosmotic coupling requires a proton gradient across the inner mitochondrial membrane. Conformational coupling depends on a conformational change in the ATP synthase. Chemiosmotic coupling mechanism. What is chemiosmotic coupling? It is the mechanism for coupling electron transport to oxidative phosphorylation. As I said, it requires a proton gradient across the inner mitochondrial membrane. Now, originally proposed, the chemiosmotic coupling mechanism was based entirely on the difference in proton concentration between the intermembrane space and the matrix of an actively respiring mitochondria. Now, in other words, the proton or hydrogen ion H+ gradient across the inner mitochondrial membrane is the crux of the matter, and is the most important issue. Now, the proton gradient exists because the various proteins that serve as electron carriers in the respiratory chain, they have two properties. These 4 membrane-bound complexes, they have two properties. First, they are not symmetrically oriented with respect to the two sides of the inner mitochondrial membrane. And second, nor do they react in the same way with respect to the matrix and the intermembrane space. If we take a look at this figure, Note that this figure 2015, creation of a proton gradient in chemiosmotic coupling, is a repeat of figure 20.8 with the addition of the flow of protons. And if you go back to figure 20.8, you will notice it's the same, but this one we added here the flow of protons. So and the arrow shows you the flow of electrons in this way. Now, as a result of transport of electrons from NADH to FMN to iron sulfur, 4 protons are pumped out of the matrix. Now notice that the number of protons is a controversy, but here, but this figure shows us an estimate for each complex. It shows us an estimate of in the process of electron transport, the proteins of the respiratory complexes take up protons from the matrix, as you can see here, to transfer them in redox reaction. Now, these electron carriers, namely NADH, FMN, إلى آخره, subsequently release protons into the intermembrane space, as you can see here, when they are reoxidized, creating the proton gradient. Then, when protons move from the matrix to the intermembrane space, there is the so-called proton gradient. As a result, there is a higher concentration of protons in the intermembrane space than in the matrix, which is precisely what we mean by proton gradient. إذن هذا معناته, this is higher concentration of H plus in the intermembrane space compared to the matrix. Now, the proton gradient in turn can drive the production of ATP that occurs when protons flow back into the matrix. We will see this in a moment. And then let's concentrate here. Then remember that the number of protons pumped out of the matrix in complex 1, 4. The number of protons pumped in complex 3 is 4. Where is complex 2? It is not shown because no pumping of protons occur in complex 2. That's why it's not shown. Then the number of protons pumped in complex 4 is 2 protons, you see? So the total number of protons pumped, 10 protons, remember, 10 protons. Now, the way in which the proton gradient leads to the production of ATP depends on the ion channels through the inner mitochondrial membrane. These channels are a feature of the structure of ATP synthase. Now, protons flow back into the matrix through ion channels in the ATP synthase. The FO part of the protein is the proton channel. Then again, protons flow back into the matrix through channels in the FO unit of the ATP synthase, and flow of protons is accompanied by formation of ATP, which takes place in the F1 unit. And لاحظوا, we will see this figure in figure 20.18. Notice here we have formation of ATP accompanies the flow of protons back into the mitochondrial matrix. Then, to summarize, at the beginning, as a result of electron transport between these electron carriers, NADH to CoQ to cytochromes, and finally to oxygen, as I showed you, each complex will pump a number of protons so that protons in the matrix decrease, proton concentration in the intermembrane space increase. So this is called proton gradient, here higher, here lower, you see? Now later on, these protons must flow back to the matrix, like through what? Only through the ATP synthase. They cannot go back except through this ATP. This is the linker. That's why we said, this is a coupling. It couples agent, coupling oxidation and phosphorylation. So protons flow through the FO portion of the ATP synthase, and then because from high concentration to low concentration, it is with concentration gradient, enough energy is produced to phosphorylate ADP to ATP, as we will see. Then, depending on that, we can say that a reasonable mode of action for uncouplers can be proposed in light of the existence of a proton gradient, such as this. Now, dinitrophenol is an acid. Its conjugate base, dinitrophenolate, is anion. It is negatively charged. Is the actual uncoupler because it can react with these protons in the intermembrane space, reducing the difference in proton concentration between the two sides of the inner mitochondrial membrane. Then, negative charge reacts with positive charge, reducing the concentration and reducing the difference between them. And they say that the proton gradient is overcome. The antibiotics uncouplers, which we mentioned, gramicidin A and valinomycin, these are themselves ionophores. They are called ionophores. What does ionophores mean? Substances that create channels for ions to pass through the inner mitochondrial membrane. They not only pass protons, but also passes potassium ions, sodium ions as well. Now, by doing this, the proton gradient again is overcome, resulting in uncoupling of oxidation and phosphorylation. Conformational coupling mechanism. Note that in conformational coupling, the proton gradient leads to conformational changes in a number of proteins, including the ATP synthase itself. There are 3 sites for substrate on ATP synthase and 3 possible conformational states. Even in conformational coupling, the proton gradient leads. Recent evidence appears to show that the proton gradient is involved in the release of tightly bound ATP from the synthase as a result of this conformational change, as you will see in the following figure. Now remember, we have, as I said, there are 3 sites for substrate on ATP synthase and 3 possible conformational states. O for open, low affinity for substrate, L for loose binding, not catalytically active, ADP and PI bind at a site in this conformation, and T for tight binding, catalytically active, ATP is bound at a site in this conformation. Then, again, there are 3 sites for substrate on the synthase and 3 possible conformations. Now, let me show you conformational states. Interconvert as a result of proton flux through the synthase that converts T to O, releasing ATP, L to T, which produces ATP. More recently, it has been shown that the F1 portion of ATP synthase acts as a rotary motor. Then, now, what happens here? If we look at the top here, You see? If we look here at the top, at any given time, each site is in one of three different conformational states. These sites interconvert as a result of the proton flux through the synthase, as I showed you. ATP already formed by the synthase is bound at a site in the T conformation. إذن في عندي in the T, remember, in the T conformation we have ATP already formed by the synthase is bound here at the T site, while ADP and PI bind at a site in the L conformation. Now, as a result, a proton flux converts the site in the T conformation. T is converted to O. The T is converted to O conformation, releasing this ATP. Then T is converted to O, releasing ATP, as you can see. Now, the site at which ADP and PI are bound, this one, assumes the T conformation from L. It becomes T, as you can see, T conformation, which can then give rise to ATP. Then a new TP is synthesized. So bound ATP is released and a new ATP is synthesized, as you can see here. More recently, as I said, it has been shown that the F1 portion of the ATP synthase acts as a rotary motor. Now, in essence, the chemical energy of the proton gradient is converted to mechanical energy in the form of rotating proteins. Now, this mechanical energy is then converted to the chemical energy stored in the high energy phosphate bonds of ATP.